Hello everyone. So let's continue. So this time, in my previous video, I have just talked about the generation of three-phase voltages and how they are connected. So let's take the star connection. So three-phase star connection. So I have three voltages. So VA, VB, VC, which are given by the expressions Vmax sine omega t, Vmax sine omega t minus 2 pi by 3 and Vmax sine omega t minus 4 pi by 3. So this is a set of, so this is in volts. There is a set of three voltages which are displaced in phase by 120 degrees. So these three voltages are electrically connected as follows. This is a star connection fashion. So that is, this is VA and let's call this as VB. Let's call this as VC. And I connect in such a way that all the negative terminals of VA, VB, VC are all connected to a common point, which I'll call it as N. And the positive terminals are taken out like this. And this one I'm calling it as A, B, and C. Now you might ask a question: why VA, VB should be here? Why this cannot be VB? So in that case, this naming will be: this is A, this will become C, and this will become C. This is just a matter of drawing the circuit diagram. All right. So now I would like to define what is called as the phase quantities and line quantities. So so if I define the current here, so imagine that these three terminals are supplying to a load. So in fact, let me draw the load. Now, what is inside this three-phase load is what we'll discuss later. In fact, load itself can also be connected as star connection or delta connection. We'll come to it later. So let's take this as the current IA and this as the current IB and this as the current IC, because this terminal is C, this terminal is B, and this terminal is A. Now these are called line currents. So these are line currents because these are the currents flowing in the line. Whereas this part is one A phase, this part is B phase, this part is C phase. So this is IA, IB, and IC. These are called phase currents. But then if you notice, the line current and phase current are nothing but the one and the same. So that is because we are the connection we are doing it is a star connection. So IA is equal to IA here. So these are phase currents. So immediately from this diagram we can notice that in star connected source, phase currents equal to line currents. Now let's talk about the voltages. So if I take a voltmeter and then if I take this as the neutral point and then with reference to this, if I measure the voltage here, so this is voltmeter, so I'll be measuring the voltage of VA. Similarly, I keep this fixed and then I take the voltmeter and then measure it across this one, I'll measure VB. And similarly, for the same, I can measure VC. So the voltages measured with respect to N are nothing but the phase voltages, VA, VB, VC. Whereas line voltages are different. So if I connect a voltmeter here between the, this is voltmeter, between the phases A and B such that plus minus terminals are connected like this. So I am interested in measuring the voltage of this point with reference to this point. So there you see there are two things coming into picture. So let's denote this as VAB. So what are the line voltages? So instead of drawing a voltmeter, let me represent it with arrows. So this is VAB, voltage of A with reference to voltage of B. Similarly, what is this voltage? So VBC, such that this is positive side and this is negative. Voltage of B with reference to C. Similarly, this is another voltage. This is VCA. Voltage of C with reference to A. So A is the reference. Therefore, this will get positive side and this will get negative side. So what are my line voltages and what are my phase voltages? So line phase voltages are nothing but VA, VB, VC. Whereas line voltages are denoted as VAB, VBC and VCA. Now my objective is to find out what are these values. So look at VAB. So now if I want to measure VAB, voltage of A with reference to B, then if I apply Kirchhoff's voltage law from B to A, that is the procedure. So then if I go like this, first I'm going from positive side to negative side of B. So therefore I drop my voltage, so minus VB and plus VA. So is nothing but VAB. So I hope you are able to see that. So VAB is nothing but VB minus VB plus VA. Similarly, if I want to find out VBC, so voltage of point B with reference to point C. So from C, I apply Kirchhoff's voltage law and go this route. So from positive side, I am jumping to negative side. So my voltage will drop by VC. Then again my voltage will add by VB. So then I come to the P. So therefore, VBC is nothing but minus VC plus VB. So you see the pattern there. So VCA is nothing but minus VA plus VC. So I know VB, VA, all these things I know. So therefore, I can calculate VAB, VBC and VCA. So let's do it using a vector diagram. So if I want to plot, so what is VA, VB, VC? So VA, VB, VC. If I want to write it in polar form, so it's nothing but V maximum angle 0 degrees, V maximum angle. In fact, I'll be using V RMS here. So let's not confuse. Whenever I am representing in polar form, I'll be using RMS, or let's call it V. V angle 0 degrees, V angle minus 120 degrees and V angle minus 240 degrees. So this is my representation in polar form of the same equations. You know that how to do. So if I come down now, so going by that, this is my VA, angle is 0 degrees and the VB will be 120 degrees behind VA. The length will be same, so might appear slightly longer. So the length will be same and this angle is 120 degrees. Because I am going in clockwise direction, it's a negative angle. Similarly, if 120 degrees further away from this, I'll get like this. This is VC. Now my objective is to find VAB. So that is minus VB plus VA. So let's draw what is minus VB. So if this is VB, then this side will be minus VB. So then the addition of these two will be VAB. This is nothing but minus VB plus VA. Now you will notice that this total angle will be 60 degrees because this side is 120 and this entire angle will be 180, so the other angle will be 60. And then this, since the length of VA VB is same, this will exactly bisect that angle, so this angle will be 30 degrees. What about the length, the magnitude of VAB? Now you will find by mathematically solving it and all, you will find that the length will be root 3 times of VA. So whatever VA length is there, root 3 times the length will be more. So in fact, I will shortly verify it also on MATLAB. And so two things you notice. The VAB, the vector, is leading VA by 30 degrees and the length also increased by root 3 factor. So I can also write simply nothing but VA into 1 angle root 3 angle 30 degrees. So if I multiply with this particular complex number. So if I do this, whatever is the angle of this VA is already a vector. So whatever is the magnitude multiplies by root 3 times, and whatever is the earlier angle, that angle will add by 30 degrees. So then I'll get the VAB. So similarly, you can notice VBC will be whatever VB is there, root 3 angle 30 degrees. If I do this, I'll get exactly same as VBC. Let's verify that. So again, I'll write, this is my VA, this is my VB, and this is my VC. So this is 120 degrees, this is 120 degrees, this is 120 degrees. So what is VBC? Nothing but minus VC plus VB. So I'll take the minus of VC. This is the exactly opposite minus of VC, and these two have to add. So when I add these two, so I'll get a vector something like this. This is VBC. So again notice, if I go backward it is lagging and forward it is leading. So again notice the length will be root 3 times of VB, and the angle, whatever was the earlier angle of VB, in fact I can actually tell the exact angle. So VB angle was V angle minus 120 degrees, whereas VBC angle is root 3 V angle minus 90 degrees. So because exactly upwards is plus 90, downwards is minus 90 degrees, what you can see here. So similarly, you can see VCA is nothing but VC into root 3 into 30. So these are the line voltages, these are the phase voltages. So it comes like that. So shall I quickly do that? Let me do it here. So this is VA, this is VB, and this is VC. Now what is VCA? It's nothing but minus VA plus VC. So let's do minus of VA. And then if I add these two, so I get a VCA, and this one again leading by 30 degrees, and the length also will be root 3 times of VC. So whatever is the actual length, that it will be increased by root 3 times, and it is 30 degrees ahead. So therefore, if I write in star connected supply, the line current IL equal to I phase. So that means IA, IB, IC all are equal to IA, IB, IC. Basically the same things. Whereas in a star connected supply, the line voltages. So what are the line voltages? So VAB, VBC, VCA. These are the line voltages. Or I can also generally call VL equal to root 3 into V phase, and I'll just write like this, root 3 angle 30 degrees into V phase. So this is nothing but VA, VB, VC. So into root 3, into root 3, into root 3, and the angle will be 30, whatever is the earlier angle. So minus 120 plus 30, minus 240 plus 30. So something like this. So let me just quickly show you on MATLAB also how this happens. So how do you define VA? So equation 5, it is, let's take the maximum value is 10 volts. So 10 and then sine omega t. So this one is just simply 10, whereas VB will be 10 sine omega t minus 2 pi by 3. So this will be denoted as 10 angle minus 2 pi by 3, or 10 e to the power of I into minus 2 pi by 3. So this is the notation we'll use to convert into polar form. Again, you had seen this in the basics of AC videos. Similarly, VC, if I write it, it will be 10 e power I, so minus 4 pi by 3. So let me define VA, VB, VC like this, and then find out the other voltages. So let me switch over to my MATLAB window. Yeah. So, so let me define VA equal to 10, VB equal to 10 into exponent of I into minus 2 into pi by 3. So this is my VB. So you are getting the x and y components of that particular vector. So if I define it as 4 pi, and then this will be VC. So VAB is nothing but minus VB plus VA. The same thing, I'm just doing that. Now VBC is nothing but minus VC plus VB. And similarly VCA is nothing but minus VA plus VC. This is what we did in the calculations. So now I want to visualize it. So what is the magnitude of VAB, VB? So absolute value of VAB. I also want to get the angle of VAB. So how to get the angle of VAB? Angle of, so for that first I will define it as a matrix. This is just to print the result. Angle of VAB. So that is VAB. This angle will be in radians, so I will convert into degrees by doing this. So 17.321 angle is 30 degrees. This is my VAB. So VBC. So this again confirms. So 30 degrees minus 90 degrees, the angle you are seeing, the magnitude is increased. 10 was the original magnitude. So 10 into root 3 is 1.732. So therefore 10 into root 3 is 17.32. That also confirms our understanding. So VCA is again nothing but, what is the angle of CA? So let's see that. So 150 degrees. So the magnitude is same. So this thing confirms that the length of line voltage is increased by root 3 and the angle increases by 30 degrees. So we are getting VAB, VBC, VCA is equal to 17.32, 17.32, 17.32, and this is 30 degrees, this is minus 90 degrees, and this is 150 degrees. These are all in volts. So in this video we had seen three-phase star connection. In the next video, let's look at three-phase delta connection. Thank you.